Greetings, students. So, in today's lecture, we will be seeing about the cables capacitance. Okay. So, previously in the previous lectures, we have been discussing about cables and what are the types of cables we have seen. Also, we have covered your construction of your cables. Okay. So, these are the topics which we have already covered. And in today's lecture, what we'll be dealing with, we'll be dealing with the capacitance of your single core cable, capacitance of your single core cable, as well as uh, in this lecture, we'll be covering your capacitance of single core cable. Okay. So, as I said, you know about the construction of the cables. We have seen about single core cable, three core cable. So those things and all we have already seen, right? So single core cable means it will be having only one conductor, and that cover conductor will be covered with your insulating layers. Whereas in case of your three core cable, you will be having three conductors enclosed within your insulating material. Okay, so this is the main difference between a single core as well as your three core. So this is represents your three core cable, whereas this represents your single core cable. Okay, so these are the main difference. So moving on, capacitance of a single core cable. So that's what we'll be mainly seeing. So with respect to the cables, which effect will be predominant means your capacitance effect will be predominant. Okay, in your cables, your capacitance effect will be predominant. So you have to consider your capacitance effect in case of before laying out the cables. Okay, so that's the main point you have to consider. So first, you have to know about the single core cable. You know about the cables, right? So the cables will be covered by the core. The core will be covered by the insulating material. So here we can consider a lead sheet. Okay, the insulating material as a lead sheet. So this lead sheet will be always having at the earth potential. Earth potential means the voltage at this lead sheet will be zero, will be maintained at zero, or I can say it will be always at your neutral point. Okay, so at the outermost point, the potential will be zero. Okay, uh, now the single core cable has an earthed metallic sheath. Okay, that is the outer part. There's an electric field between the conductor and the sheath. This you know. So if the outer part is the sheath, which is maintained at the zero potential, okay, zero potential, and at the center part is a conductor. So this conductor will be carrying your voltage. Okay, so that is it will be having some potential. Okay, so in between uh, from the sheath to your conductor or the core, the in between part is there, right? So that part will be acting as a dielectric medium. Okay, that is nothing but your insulating medium. So now we will be seeing about the derivation part for your single core cable. Okay, that is the potential difference. What is the potential difference from here to here for a single core cable? So that's what we will be seeing in this lecture. So starting with we are talking about capacitance, right? So capacitance means you have to consider your charge enclosed. So Q equal to C into V. So this is the basic formula. So now we have to consider for per meter length. Okay, similar as I have said in your overhead transmission lines, you have to consider for per meter length. Afterwards, you have to multiply with the entire length. Okay, so that's the main strategy used. So same thing is again used over here. Let Q be the Q coulomb per meter and be the charge per meter. Okay, for per meter, the charge enclosed is capital Q. Next, what is that? This the distance you have to take. The distance for the charge you have to take. So, sorry, not the distance, the flux density. Okay, so flux density you have to take. Electric flux density is nothing but dx. for the particular distance x you have to take. So for a particular distance x means, so here it is, from R, that is the center, to a particular point x you have to consider. Okay, so over here the surface area of the cylinder you are taking. Why we are taking the cylinder means, if you are taking the what you can say, sectional view means, that is it will be like this. It will be in shape of a cylinder. It is like a cylinder. Okay, so that only you will be considering for a surface area of a cylinder over here. So it will be 2 pi x L meter square. Y means this 2 pi x is nothing but the circumference of your circle. So L is nothing but the length of your cylinder. Okay, so this will be contributing to the surface area of your cylinder. Okay, so now dx is nothing but your flux density. The flux density at radius r. Okay, at the radius r is nothing but your flux divided by your area. Okay, flux density is nothing but the flux which is present per unit area. So I won't be explaining so much regarding this. If you want to kind of go through with your EMT. Okay, so the flux is nothing but the amount of charge over the particular area. So it will be contributing to the Q value, and the area we have already found out. So it will be presented over here. So now we got for the dx. Okay, so this is for a 1 meter length. As I said, now we are considering for just per meter. Okay, so after that, the electric field intensity Ex, field intensity you have to calculate. So field intensity is nothing but flux density divided by epsilon. Okay, so E equal to D by epsilon. Its own formula. Again, you have to get with your EMT. Okay, so it will be dx by epsilon. So this epsilon, you know, it is equal to nothing but epsilon naught epsilon r. Okay, so now you have to apply the value of this dx over here. So if you're applying this, you'll be getting q by 2 pi epsilon r x. So you know about epsilon r and epsilon naught. So I no need to explain regarding that. Now next is about the potential difference from the core and the sheet. So this is the main thing what we have to we find out. Okay, as we said in the beginning itself. So you have to consider the potential difference from the outside of the sheet to the middle point of the core. Why means, at your outside, your sheet will be having the potential 0, whereas your electric core will be at some potential. So that's the thing what you have to consider. So over here, your V equal to R to R. So here, this R is nothing but the outer radius. Okay, outer radius is given by R, and this small r is nothing but the radius of your core. Okay, so the those things forms out your limits. Okay, into Ex dx. So Ex is nothing but the electric field intensity that we have found over here. So from R to R, then Q by 2 pi epsilon naught epsilon r x. Okay. So after this, here the variable is your x. Okay. So this x dx is what you have to integrate. So 1 by x dx is nothing but ln of x. Okay. Then you have to apply your limits over there. So if you're applying the limit means you'll be getting ln of capital R, that is the outside of your radius minus of the inner core. Okay, so this is what with respect to your potential. Okay, from your outer sheet to your inner core. Okay, so we got the voltage. So this voltage value we have got. You need the capacitance. Okay, so you got the Q V. So what will we do in C equal to Q by V. That's the formula over here. So you'll be applying this value of V over the denominator. So you'll be getting the Q and Q will be cancelled out. So finally you'll be getting the capacitance value as 2 pi epsilon naught epsilon r ln of R by R. Okay, so this you know how to write. I have already told up in the previous lectures how ln R minus ln R can be written at ln R by R. I have already covered it. So after this, we have to consider for the entire length. Okay, now till now we have considered for a single length. So sorry, per meter we have considered for L meters. Nothing but you have to multiply with that distance L. Okay, so this is the final formula for your capacitance. Okay, this is for a single core. For a single core. And now we have to consider for the charging current. So charging current, we have already seen how to find with respect to your capacitance in your first unit itself. The first unit itself, we have covered that. Okay. So respect to that, uh, if the conductor is not circular, okay, then what happens is that the charging current can be I equal to V by XC. So this XC is equal to 1 by omega C. So this you already know. So finally, what you'll be getting is your I value. Charging current is nothing but V phase into omega C. So omega C is nothing but 2 pi F into C. So that is this capacitance value. It will be you have to apply over here. So this will also be contributing to some dielectric losses. So the dielectric losses formula they have given PD equal to omega C V phase square sine del. Okay. So the del is nothing but 90-degree minus of your phi value. Phi, you know, is nothing the angle between voltage and current. So this is what with respect to your single core cable. So single core cable is very important question. They will be repeatedly asking in your university point of view. Okay, so with this this lecture is getting over.